Now, we continue with our second part of this chapter, which is sound wave. Now, first and foremost, we need to know how to produce a sound wave. Sound wave can be produced by vibrating object or mechanical system. Sound waves are longitudinal wave propagate in the form of compression and rarefactions in air. When sound wave produced from speaker, it vibrates, which causes the air beside the drum to vibrate here. So the compression and stretching of air particle creates a sound wave, which is carried through the air to your ear. So the speed of sound in fluid or gases or in solid materials was depend on the fluid compressibility and inertia. So the speed of sound in fluid and gas can be found by using these equations, where V is equal to square root of B, where B is the Bach modulus. You did learn about this Bach modulus in last semester, divided by the density, where this density is equal to depends to the fluid or the gas itself. While the speed of the longitudinal wave in solid rock or in any materials other than fluid and gas can be found by using this formula, where speed is equal to the square root of y divided by the density, where y is the Young modulus, and then rho is equal to density of the materials. And the relations between speed of sound and temperature is equal to this formula. So if, let's say, I need to find a velocity of the sound, or the speed of sound in temperature is equal to 50 degrees Celsius or 270 Kelvin, you can use these equations. So it is related between velocity is equal to 331 meter per second times with the square root of the T is the temperature, which the T is supposed to be in Kelvin as a unit, divided by 273 Kelvin. So you can use this equation to find the speed of sound in particular temperature. You did or you also familiar with the words of intensity of light, where usually we define the intensity of light based on the brightness of the light. So it is similar with the sound wave. There is an intensity of the sound wave in these chapters. So this intensity of sound wave was defined as a measure of the amount of energy per second that passed through a square meter of area perpendicular to the wave directions of travel. It can be written or simplified with this equation, where intensity, usually symbolized as a capital I, is equal to power divided by the perpendicular area. This hence will bring us to the SI unit of intensity is equal to watt per meter squared. Now, the value of intensity for sound wave depends on the area. So for, let's say, this sound wave was produced in a sphere of radius r with the center of S, just like this picture. So the area here will be depending or will be focused on the area of the sphere, which the formula of area of the sphere is equal to 4 pi squared. Sorry, this is supposed to be 4 pi r squared. So the value of intensity in this type of cases is depend on the value or on the equations of area. So for this case, the intensity is equal to P divided by 4 pi r squared. Now, differently, when the energy or the sound wave was radiated from the linear source falls perpendicularly on the curved surface of a cylinder of radius r, just like this picture. So the intensity will be different from the previous intensity due to the formula of area. So the formula of area for cylinder is equal to 2 pi r. R is the radius here, and h is the height here. So the intensity hence will become intensity is equal to P power divided by the area of the cylinder itself. So in conclusions, the value of intensity will be different or will be varied based on the area. So when the area is in circle, the value of I will be follow the formula of area in circle. But when the area is in cylinder, then the intensity will be follow the formula of the area in cylinder. So please take note that one. Now intensity level, the level of intensity or the stage of intensity was also can be written in decibel. You are quite familiar with this word actually. But then what is decibels? So this intensity level in decibel is the relative intensity of a sound. Is called the intensity level or decibel level, which we usually define by this equation here. So it is symbolized as a beta is equal to 10 log of the divisions between intensity of the sound that been produced divided by the reference intensity, where the value of reference intensity is constant. The value is equal to 1.0 to the power of negative 12 watt per meter.
Now, this is our last subtopic for these chapters. It is called as a Doppler effect. Now, have you ever wondered, let's say if a car or truck is moving while its horn is blowing, the frequency of the sound you hear is higher as the vehicle approach you and lower as it move away from you. This phenomenon is one example of the Doppler effect, which is named from the Austrian physicist Christian Doppler, who discovered it. And the same effect is heard if you are on a motorcycle and the horn is stationary. The frequency is higher as you approach the source and lower as you move away. So Doppler effect is actually when the frequency of sound wave remain constant as long as the listener and the sound source remain stationary. But then, when there is relative motion between the observer and the source, there is a change in frequency of the sound heard by the observer. Now, this phenomenon is called the Doppler effect. Doppler effect was divided into three cases. The first case is when the observer is moving relative to a stationary source. The second one is the observer when the observer is moving relative to a stationary observer. When the source is moving relative to a stationary observer. And last but not least is general case. Now, for the first case where the source is moving and stationary or the observer is stationary, the observed frequency or the frequency that heard by the observer can be calculated by using these equations, where FO, this is stand for observer frequency, is equal to V of the air, velocity of the air or speed of the sound in air, divided by the speed of sound in air plus minus with the speed of the source and times with the frequency of the source. Now, I will explain more on how to use these equations in examples of the Doppler effect. So please watch it and learn from it. And on the case 2 or the second case where the observer is moving while the source is stationary, the observed frequency where FO is equal to the speed of the sound in air plus minus with the speed of the observer divided by the speed of sound in air and then times with the frequency of the source. So that's it for this chapter. Once again, I need to remind you to watch all the examples that I provided to you because some of it might come out in your final or in your midterm. So good luck for this chip.